This is Chapter 2, Part 1, Speed and Velocity. And here we see a sprinter coming out of the blocks. This is a moment of great acceleration, which we'll learn about later. And then after he accelerates, he'll be running at constant velocity. And we'll be talking today about distance, displacement, speed, and velocity to help us prepare to understand acceleration later in Chapter 3. Position, distance, and displacement. Before describing motion, you must set up a coordinate system, that is, define an origin and a positive direction. And so here we have a guy walking eastward, or we could say he's walking in the positive direction. We define an origin, and here the origin is just that tree over there on the far left. It doesn't mean that he has to start his walking at the origin. But the origin is going to define positive and negative directions. Everything is in reference, in relation to that origin. Then we have his initial position marked as xi, and we have his final position marked as xf. And so he's walking from an initial position to a final position. The distance is the total length of travel. So if you drive from your house to the grocery store and back, you have covered a distance of 8.6 miles. So let's trace that out. You drive from your house to the grocery store and back. That's 4.3 there, 4.3 back, which is 8.6 miles. Total distance of 8.6 miles. Displacement is the change in position. If you drive from your friend's house to the grocery store and then to your house, your displacement is 2.1 miles in the positive direction, but the distance you have traveled is 10.7 miles. So let's trace that out. We're going to drive from your friend's house to the grocery store, and notice that that's 2.1 plus 4.3, so 6.4 miles. And then after the grocery store, we drive to your house. That's another 4.3 miles. So 6.4 plus 4.3 is 10.7 miles. Total distance of 10.7 miles. So why is the displacement only 2.1? Because displacement always takes into account the point of origin and the direction. And so if we're going in the positive direction, considering this kind of diagonal direction here, and we see the x-axis that I'm circling now with the mouse arrow, right? So motion along the x-axis is positive. Well, the displacement from the origin of your house in relation to the friend's house is 2.1 miles. 2.1 miles in the positive direction. So even though your distance was much more, 10.7 miles, your displacement was only 2.1 because you ended up only 2.1 miles away from your friend's house. So that's the main difference between distance and displacement. Displacement takes into account direction and an origin, whereas distance has no regard for either of those. It doesn't care where you started, doesn't care where you ended up, or even what direction you're going. Distance is just total, the total units of length covered. And displacement is the net change in position from the final position in relation to the initial position. All right, let's suppose, just to kind of build on this, if you start at your house, go to the grocery store and come back, that's 8.6 miles distance. All right, I'll say that again. You start at your house, go to the grocery store, and come back. 8.6 miles of distance. What is your displacement? You know your distance is 8.6 miles. Started at your house, went to the grocery store, and came back. So my question to you is, what is your displacement? Think about that for a second. Come up with your answer. You should have thought of this. Your displacement is zero. Zero. Because you ended up exactly where you started. And so your displacement is zero. even though your distance is 8.6 miles. This is a very blocky kind of drawing, but it gets the point across. We're going to define the stoplight as the origin, and we're going to define the initial position of the car as xi, and the final position of the car as xf. And now, take a look at this notation that you should have seen before, but just in case you didn't, let's talk about it right now. This is called delta notation. And so that triangle in front or to the left of the x means delta, the Greek letter delta. And when you see delta in physics, it means difference in. Delta is difference. They both begin with D. That helps to remember. Delta is difference. And delta x is the difference between the final position and the initial position. Now, delta, you should keep this in mind, is always final minus initial. It's not initial minus final. All right, so anytime you see delta, you should automatically think final minus initial. So to clarify, xi and xf are positions. They are positions. But delta x is the displacement. The displacement is the difference in position. The displacement is the difference in position. Let's talk about speed. Any combination of units for distance and time that are useful and convenient are legitimate for describing speed. So miles per hour, you're used to those. Kilometers per hour, they use those in Canada and Europe. Centimeters per day, plants sometimes, fast-growing plants grow in centimeters per day. Light years per century. So all of these are, you have a distance unit per time unit, and so these are speeds. A cheetah is the fastest land animal over distances less than 500 meters and can achieve peak speeds of 100 kilometers per hour. All right, so a cheetah, even though it doesn't have nearly as much endurance as a horse, right? If you ever raced a cheetah and a racehorse on, maybe a half-mile track, the horse would just leave it in the dust, and the cheetah would be panting, ready to collapse, because cheetahs don't have much endurance, but they have an extreme amount of speed. And so once they get going, their peak speeds can be up to 100 kilometers per hour. Let's talk about position time graphs. The data in the table can be represented by plotting the time data on a horizontal axis and the position data on a vertical axis, which is called a position time graph. So here on the left column we see times, and on the right column we see positions. And so this is a table for a moving object, and at time 0 it has covered no distance, so position is 0. At time 1 second has gone by, it's gone 5 meters. 2 seconds have gone by, 10 meters. 3 seconds have gone by, 15 meters, and so on. Now here's what the graph looks like. This is a position time graph. A position versus time graph is also called. And so we see on the y-axis the position, meters, and on the x-axis the time, seconds. And each of the points in the table is represented by a dot on the graph. And you can see that at 1 second we've got position of 5, at 2 seconds position of 10, 3 seconds position of 15, and so on. Now, the reason that it's helpful to do graphs like this is because if you look at the slope of this graph, it represents something that is involved with motion that we just talked about, and that is speed. The slope of a position time graph is the speed. The slope of a position time graph is the speed. Now let's understand why that's true. Slope is rise over run. Okay, and so let's just look at this initial portion of the graph. All right, just up to the first dot. Well, the rise is 5 meters. The run is 1 second. 5 meters over 1 second is 5 meters per second. Or let's look at this next portion, the second dot. Well, if we're looking from the first dot to the second dot, Well, the rise between those 2 points, we go from 5 to 10. So the rise is 5 meters. And the run, since we go from 1 to 2, the run is 1 second. 5 meters divided by 1 second is 5 meters per second. And so we can see that the slope of the position time graph is the speed. And as you've probably figured out by now, this particular slope is 5.0 meters per second. 5.0 meters per second. And just a reminder, whenever you're looking for the units of slope, all you need to do is look at the units of your y-axis, which is m in this case. And then you look at the units of your x-axis, which is s in this case, and then you just put one over the other. And so m over s is meters per second. So here we can clearly see that the slope of this graph is the speed. Now let's talk about speed time graphs. So the data from the previous slide can also be represented by a speed time graph. This would be the speed time graph. Notice that here on the y-axis, instead of position, we have speed. And so the units on the y-axis are meters per second. That's a speed unit. And then the x-axis is still time in seconds. Now notice that we have a straight line here. Why the straight line? Because the y-axis represents speed. And since the speed that we've already found from the previous slide is 5 meters per second, and that's a constant speed, notice that at each second, we are still at that same speed of 5.0 meters per second. We're still at the same speed of 5.0 meters per second. It doesn't change. And so each of these dots is on that line of 5.0 meters per second. Now let's interpret what this means. So this means that at 1 second, the moving object has been traveling at 5 meters per second. And so therefore, it has covered 5 meters. At 2 seconds, this moving object has been traveling at 5 meters per second for 2 seconds, and therefore it's traveled 10 meters. All right, so you should be able to, think about what this blue square means. This blue square is the area under the speed time graph. The area under the speed time graph. And my question to you is, what does that area under the speed time graph represent? Think about that just for a second. Don't worry if you don't know the answer, but just think about it. What does the area under the speed time graph represent? Well, here's the answer. The area represents the distance traveled. And that makes sense because look at this, let's look at this rectangle again. And let's say we want to know how far this moving object has gone in 6 seconds. Well, we've got 6 seconds as our x-axis, and we have 5 meters per second, the whole 6 seconds. And you know that distance times velocity is time. And so we have 6 seconds times 5 meters per second, and that gives us 30 meters. Okay, so I'm circling now with a mouse arrow the 6 seconds, and I'm circling now with a mouse arrow the 5 meters per second. Well, the area of a rectangle is length times width, and so the length is 6 seconds, and the width, or the height, is 5 meters per second. 6 seconds times 5 meters per second is 30 meters. Okay, write that in your notes. 6 seconds times 5 meters per second is 30 meters, and that's because the seconds cancel. And once again, you can use the units on your graph to confirm that. The units on your y-axis are meters per second. The units on your x-axis are seconds. And if you're doing an area, it's going to be these x-axis it's going to be these x-axis units times these y-axis units, and s times m over s gives you just m because the s's cancel. All right, average speed. If we know average speed and travel time, the distance traveled is easy to find. Total distance covered equals average speed times travel time. So d equals vt. In Algebra 1, you learned d equals rt, or rt equals d. Rate times time equals distance. And this is exactly that same formula, d equals vt. For example, if your average speed is 80.0 kilometers per hour on a 240-minute trip, what distance do you cover? All right, so before you just try to do this problem on your own, remember that you're going to use d equals vt, of course. But also remember that since the speed is given in kilometers per hour, and the time is given in minutes, you definitely need to convert those minutes to hours first. All right? All right, so pause the video, get the answer, and then resume. You should have come up with 320 kilometers. All right, because 240 minutes is 4 hours, and then 80 times 4 is 320, so 320 kilometers. In a trip by car, the car will certainly not travel at the same speed all during the trip. The driver cares about the average speed for the trip as a whole, especially for long trips. This is what matters. So the average speed equals the total distance covered divided by the total travel time. For example, if I drive 100 miles in 2 hours, including stops, maybe I stop to get gas or stop to use the bathroom, accelerations, because, you have to speed up to that speed limit or slow down when you get off the highway. Right, but including all that, I do the 100 miles in 2 hours. Then my average speed is 50 miles per hour. It's simply 100 divided by 2. If a plane flies 3,000 miles in 5.51 hours, what is its average speed? Pause the video, do that on your own, and resume when you have your answer. All right, you should have got 544 miles per hour. You should not have gotten 544 point something something something. Why? Because, once again, significant digits. This is division, 3,000 divided by 5.51. And when you do 3,000 divided by 5.51, you realize that your least known term has 3 significant digits, and so your final answer has to have no more than 3 significant digits. All right, let's take a look at this diagram. We have a car going 30 miles an hour for 4 miles, and that takes T1 hours. And then we have that same car going 50 miles an hour for 4 miles, and that T2 hours is how long that part of the trip takes. And so here's the question that you have to think about. Is the average speed of the red car 40.0 miles an hour, more than 40.0 miles an hour, or less than 40.0 miles an hour? Now, I'll tell you this, most students simply look at this and think to themselves, oh, all right, he was going 30 for half the trip, 30 miles an hour for half the trip, and 50 miles an hour for half the trip, and so we're putting them together, taking the average, so it must be 40 miles an hour. No, that is not the answer. And I'm putting this because this is a skill that you're going to need in physics. You got to think about things. And so I'll tell you this, the answer is not 40 miles an hour. It's either going to be more than or less than. So I want you to think about that. I'm not asking you to calculate. No calculation. Just think. All right? Is the average speed, the overall average speed for this 8-mile trip, 8 miles, 4 plus 4 is 8. All right, is the average speed more than 40 miles an hour or less than 40 miles an hour? Pause the video, think that through, and then resume when you have your answer. Less, that is the answer. So the average speed will be less than 40 miles an hour because the car spends more time at the slower speed. Okay, so we know that the average speed for this 8-mile trip is going to be less than 40 miles an hour because the car spent more time at the slower speed. However, it's good to prove this by calculating what that actual average speed is. Now, those of you who have pretty good math skills should be able to do this on your own and actually calculate the average speed. So I encourage those people to challenge themselves and pause the video and figure this all out on your own until you have a specific numerical answer for your average speed. But if your math skills are weak or you just feel you're rusty, then carefully watch the video as I go through the proof and the calculation step by step. Here's proof that the average speed is less than 40 miles per hour. The total time is t1 plus t2 hours. The total distance is 8 miles. Therefore, the average speed is 8 over t1 plus t2. So 8 miles over t1 plus t2 hours. Recall that d equals vt. So d1 equals v1 t1 and d2 equals v2 t2. Therefore, t1 equals d1 over v1 and t2 equals d2 over v2. Now d1 is just 4 miles and d2 is just 4 miles. And v1, we know that's 30 miles an hour. v2 is 50 miles an hour. And so what we're doing here is, since we don't know t1 and t2, we're just putting them in other terms. So we can replace 8 over t1 plus t2 with the following expression. 8 over d1 over v1 plus d2 over v2. We simply replaced t1 with d1 over v1, and we replaced t2 with d2 over v2. And the final step, we just plug in what we know. d1 and d2 are both 4, so we put the 4's in. v1's 30, v2's 50, and when we do this on our calculator, we get 37.5 miles per hour. And that is the answer, and as you can see, it's less than 40 miles per hour. Instantaneous speed. A car does not always move at the same speed. You can tell the speed of the car at any instant by looking at the car's speedometer. The speed at any instant is called the instantaneous speed. And as you drive, you've noticed this, right? At any second, you could be going, 20 miles an hour, and then you're at 21, and then 22, and then 23, or you could be slowing down, but your speed is changing. So the instantaneous speed is the speed at any instant. Now, velocity. Velocity is a quantity that specifies direction as well as magnitude, and so it is a vector quantity. A velocity, like force, is a vector quantity. We have magnitude and direction. Speed, on the other hand, is simply a scalar quantity, and I talked about vectors and scalars in the last video. Speed, all we care about is the magnitude and not the direction. Constant velocity. So constant speed means steady speed. Something with constant speed doesn't speed up or slow down. Constant velocity means both constant speed and constant direction. Okay, so constant direction is a straight line, and constant velocity means motion in a straight line at constant speed. Alright, so this is just the definition of constant velocity. It's pretty simple. Constant velocity simply means that the magnitude remains the same and the direction remains the same. If either the speed or the direction or both is changing, then the velocity is changing. Alright, so imagine you're driving a car around a circular racetrack. Well, as you go around a turn, your direction is changing, and your speed may or may not be changing. You might be accelerating out of a turn or decelerating into a turn, and in that case, your magnitude and velocity, or your magnitude and direction of the velocity, both are changing. Constant speed and constant velocity are not the same. A body may move at constant speed along a curved path, but it does not move with constant velocity because its direction is changing every instant. So look at this merry-go-round here, okay, or carousel. Well, once the thing gets going, for however many minutes the ride lasts, suppose it lasts 3 minutes. Well, during that time, it's going at a constant speed. But we would say that it's not constant velocity, and that's simply because the direction in that circular path is constantly changing. The direction is constantly changing. It's not straight line motion. And so even though the magnitude of the velocity stays the same for these carousel riders, the direction of that velocity is constantly changing. Average velocity. Average velocity equals net displacement divided by elapsed time. If you return to your starting point, but your average velocity is 0. Okay, so let's say that you start at 0, you sprint 50 meters, and then you walk back to that point of origin, the 0. Well, it turns out that your average velocity is 0 because your net displacement is 0. And obviously you sprinted hard and then you walked back, and so you covered distance. But since your net displacement was 0, as we talked about before, like with that house and grocery store example, net displacement is 0. Well, 0 divided by any elapsed time is still 0, and so your average velocity is 0. So this guy who sprints 50 meters and walks back has an average velocity of 0. However, his average speed is definitely not 0, right? His average speed is not 0 because speed is a scalar quantity. But his average velocity is 0 because velocity is a vector quantity. And velocity depends on net displacement, whereas speed only depends on distance. All right, so what's the total distance for this guy's trip? Well, it's 100 meters because he goes 50 meters in the positive direction and then 50 meters in the negative direction. But that's a total distance of 100 meters. And yet it's a net displacement of 0. This is an animation to help us visualize position, velocity, and acceleration. We're not going to worry about acceleration right now. We'll be covering that in Chapter 3. But even though some of this might seem basic, it's very good to lay a solid foundation before we learn about acceleration. And then also, overall, it's good to have a good foundation on in position, velocity, and acceleration, because so much of physics, especially what we're going to do during the first semester, so much of it depends on our understanding of these concepts. All right, so going back to position. All right, so right now his position is 0 meters. Let's say I move him. Well, if I move him, then his position is now about 2 meters, 1.95 meters. I can also move him backwards. And if I move him backwards, his position right now here is about negative 2 meters, negative 1.95 meters. And so that's just position, all right? And so remember that displacement is the difference in position. And so he went from 0 to negative 2, for example, here, and so his displacement would be negative 2 meters. Now let's suppose that his starting position were negative 2, and his ending position were 2. Well, then his difference in position would be 2 minus negative 2, and that is a total of 4 meters. All right, so remember that displacement is just difference in position. Okay, now let's reset it and see what it looks like when we give him a little velocity. So we're going to give him a velocity of 1 meter per second. And note that this is a positive velocity. And you should already be thinking, well, then that means he's going to go to the right, because the right is the positive direction. And so let's just play it and see what happens. He's moving along in the positive direction at 1 meter per second. Now let's replay. And now you're going to see, just to help reinforce your understanding, notice that as each second goes by, he's covered 1 meter. And that's exactly what 1 meter per second means. And let's count it out. 1, 1,000, 2, 1,000, 3, 1,000, 4, 1,000, 5, 1,000, 6, 1,000, 7, 1,000. Notice as I was counting, that each time I said a second, he was finishing another meter. All right, so that's just to reinforce the concept of meters per second, which is a measurement of velocity. Okay, now let's go to these graphs here, and let me show you what that motion looks like with two graphs. In this video we've learned about position time graphs, and we've learned about speed time or velocity time graphs. And so even though there is an acceleration graph here, we're going to ignore that for now. What I want you to concentrate on for now are the position and velocity graphs. We're going to give him, again, a steady speed of 1.00 meters per second. And it's going to be in the positive direction. And now watch what happens when I play. Look at the graphs. Well, they're as you would expect. What we have here, the position time graph, has a slope. It's a straight line, and obviously the slope of this line is going to be 1 meter per second. Now you can see that right at this point. Okay, so right now I am indicating a point there, and you see where I've got the mouse arrow hovering. Well, if you look at that point corresponds to a position of 5 meters. And note that that point also corresponds, dragging the mouse arrow down, also corresponds to a time of 5 seconds. And so it's done 5 meters in 5 seconds. The rise is 5 meters, the run is 5 seconds, and that is 1 meter per second, because 5 divided by 5 is 1. So notice how we have the position time graph here. That is a slanted line. But now notice we also have this velocity time graph. And like the other one I showed you, that's a straight line, because at every second the velocity hasn't changed. It's a constant velocity of 1 meter per second. Now let's give him a slightly faster velocity. And well, let's just reset it first. And let's give him a faster velocity, and let's see what happens. Okay, notice we still have the two lines. Boom, he crashed. All right, but let's look at the point. Let's look at the line here. Notice that this blue diagonal line is steeper, and steeper means that it has a greater slope, and that greater slope corresponds to a greater speed, because now he's going at 2 meters per second instead of 1 meters per second, and that means that the slope of this diagonal blue line segment, that slope is 2. Notice also that we have our velocity time graph, and it's still a straight line, but that straight line is now at 2 instead of at 1. All right, don't worry about all these weird things that happen after the crash. That's not important. We're just focusing on the things that happen before his crash. And let's do one last one and see what happens when he goes at 5 meters per second. Notice how steep the blue line is now, because it's a higher slope, and you have for every second you have it rising 5, because I had put it at 5 meters per second. So at 1 second we already have covered 5 meters. So we have a steep slope for the blue line segment, and we still have the flat line for the velocity time curve, because the velocity is constant, it doesn't change, and that's represented by a horizontal line. It hovers at 5 meters per second for the duration. Now, if you were to take the area under this red line, the area for the interval from 0 to 2 seconds, well, that would give you his total distance. His total distance covered is the area under this curve. And so this would be 5. That's your height. Your length is 2. 5 times 2 is 10 meters. The area under the velocity time graph represents the distance covered. And sure enough, we can see here in the position graph that we're dealing with a distance of 10 meters. And you can see it graphically here where I'm hovering with the mouse arrow. You can see that that is 10 meters, which was reached at 2 seconds. And 10 meters is the same as the area under the red line. Instantaneous velocity. This plot shows the average velocity being measured over shorter and shorter intervals. The instantaneous velocity is tangent to the curve. Now, let me talk about this for a little bit, because it might be something that you're not so familiar with. So we can see that if we're looking at the interval t1, t2, right, a certain amount of time has elapsed between time t1 and time t2. That would be your run. And then your rise is the difference in in position between t1 and t2. And so rise over run is slope, as we've already said, and that gives you your speed. Now, the reason we're talking about average velocity here is because, as you can see, the blue line is curved, whereas the green line is straight. And so we speak of slope when we're talking about a straight line. And so what we're talking about here, if you look at T1 and T2, okay, so between T1 and T2 we have a curved blue line and a straight green line. And so the straight green line is called, or refers to, the average velocity between those two times. And even though the velocity is changing, there's still an average, and the average, you get that just by connecting the two endpoints with a straight line. The same is true with the interval t2 to t3. All right, so between those two times, we can see that there's also a curved blue line because the velocity is changing. But if you look at the green line that connects the two endpoints, well, we can see that that green line has a slope. And the run of that slope, and I'm highlighting that green line right now with the mouse arrow, the run of that slope is the time that elapsed between T2 and T3. But the rise, which I'm tracing now with the mouse arrow, is the difference in position between T2 and T3. Because you know on this graph the y-coordinate represents position, whereas the x-coordinate represents time. And that brings us to the slope of the tangent line. Notice that this green line here, this long green line here, is tangent to the blue curve. And tangent means that it touches at only a single point. And so this tangent line, the slope of this tangent line, represents the instantaneous velocity at time t3. Obviously the velocity is continually changing, as we see by this curved line, but at that particular instant of t3, the slope of the tangent line represents the instantaneous velocity. Now, a lot of this stuff is covered more in calculus, and you don't have to worry about it so much now. Those of you who are in calculus currently will probably see this or have seen it already in your class. If you aren't in calculus yet, don't worry about this. This isn't a concept that I'm going to be testing on, but it is something that's interesting and worth pointing out. One more slide on instantaneous velocity, and this just helps to understand the tangent line thing a little bit better. All right, so let's we have a series of green line segments here, and let's look at how these green line segments indicate average velocity. All right, so our origin is here. This is a position versus time graph, and let's look at this first green line segment where it says VAV equals 13.7 meters per second. Well, all they did there is they connected the dots. All right, so there's, if you look at this blue line, the beginning dot is right at the O, and the ending dot is the point that I'm indicating now with the mouse arrow. That's the ending dot, and the line segment simply connects the dots. Because even though this blue line has been, changing direction and it's a curve, well, there is still a total elapsed time, and that would be the run, and there's still a total position change, and that would be the rise. And so the average velocity between time 0 and time 2 seconds is 13.7 meters per second. And they got that, really. You can just prove it to yourself, because if you look at this line here, okay, so I'm kind of tracing out a line right now with the mouse arrow. Well, you can see that that corresponds to about 27 or 27.5. And so we have a rise of 27.5, a run of 2 seconds. Do that on your calculator and you'll get something close to 13.7 meters per second. Okay, now the next line segment, as you can see, it's shorter because we've narrowed the interval. Now, instead of the interval being 2 seconds long, it goes from about 0.25 seconds to about 1.75 seconds, and that's obviously shorter than 2 seconds. And we also have a starting position of 10. You can see that that's 10, starting position of this green line segment, and the ending position is at about 27.5 again. All right, and so the rise is going to be the difference between 27.5 and 10, and the run is going to be the difference between the ending time, which is about 1.75, and the beginning time, which is about 0.25. And so we're still going to have an average velocity, as you can see, that is 12.1 meters per second. It's close to 13.7, but it's not exactly because we've shortened the interval. Now, look at this interval. We've shortened it even more, and it's even closer to 12.1. And then we have on a final interval here that's even closer. Notice that as we make the intervals smaller and smaller, and I'm talking about the time intervals, as we make the time intervals smaller and smaller, smaller and smaller, or narrower and narrower, notice how the slopes of these green line segments gets closer and closer to the slope of the tangent line. And the slope of the tangent line at 1 second, the slope of the tangent line at the point represented by t equals 1 is 10 meters per second, 10.0 meters per second. All right, so the tangent line is, as you can see by these intervals that approach and get closer and closer to a single point, the slope of the tangent line represents the instantaneous velocity. Let's talk about motion in one dimension by doing a sample problem. Light from the sun reaches Earth in 8.3 minutes. The speed of light is 3.0 times 10 to the 8th meters per second. How far is Earth from the sun? Pause the video, do this on your own, and resume when you have your answer. You should have come up with this. Velocity is given, 3.0 times 10 to the 8th meters per second. 8.3 minutes is given, and that's 498 seconds. You just multiply 8.3 by 60. And then finally, d equals vt. So you do your plugging and chugging, and you end up with 1.5 times 10 to the 11th meters. Let's do another problem. Jeb maintains a constant velocity of plus 5.00 meters per second. At time t equals 0.0 seconds, Jeb is plus 250 meters from point A. How far is he from point A after 60.0 seconds? Alright, so you're given his initial position and his final position. You should be able to figure this out. So pause the video and do it on your own, then resume when you have your answer. Let's go through the solution, and it helps by showing you this graph. You don't have to do a graph in order to solve the problem correctly, but the graph helps with explaining the problem. Okay, so this is the position versus time graph, and we're given that Jeb starts at position 250, and we're also given that he travels 60 seconds at 5 meters per second. And so, if he's going 60 seconds at 5 meters per second, that's 60 times 5, which is 300 meters. So it's the seconds cancel. And then 300 meters added to his initial position of 250 gives us a final position of 550 meters. This position time graph depicts Chris's movement up and down the aisle at a store. The origin is at one end of the aisle. What is Chris's average velocity between 37.0 seconds and 46.0 seconds? Now, you might wonder, how are you going to deal with these weird numbers? Well, just don't freak out and look at the graph. Notice that we have, if you look at this line that I'm tracing now with the mouse arrow, tracing up and down, well, that would be at time 35. So 37.0 is right at this point, where instead of being a flat line, it's now a slanted line. And then 46.0 is right at this point that I'm tracing now with the mouse arrow. So 46.0, we can see that between 37.0 and 46.0, we have a straight line. We have a straight line that represents his change in position in relation to time. And so for this problem, you're going to have to use the delta stuff. Okay, delta means final minus initial. And remember that slope is rise over run. And so you should be able to figure out the slope of this line segment that goes from 37.0 to 46.0 seconds. You should be able to find the slope because you can get the rise over run. Pause the video, do this on your own, and resume when you have your answer. All right, let's go through the solution. And so what we need to find is the average velocity between 37 seconds and 46 seconds. And so we're looking for the slope of this line segment that I am tracing now with the mouse arrow, that line segment. And that slope will give us the speed. And so since we need rise over run, well, our rise is delta x, or change in position, and our run is delta t, or change in time. And then keeping in mind that delta is always final minus initial, I can set that up as xf minus xi over tf minus ti. And then you just do your, what I like to call, plugging and chugging, where you plug in numbers and then chug through the calculation. And so we have 3.0 minus 12.0. Where does that come from? Well, my final position is 3.0 meters, as we can see here on the graph. And my initial position is 12.0 meters, as I can see on the graph. And then we also have final time minus initial time. Final time 46 seconds, initial time 37 seconds. And when we do this calculation, we end up with negative 1.0 meters per second. Notice that the final answer is in two significant digits, because if you look at the numerator here, well, 3.0 minus 12.0 gives you negative 9.0, and then down here 46.0 minus 37.0 gives you 9.0, and so negative 9.0 divided by 9.0 gives you negative 1.0 meters per second. And so this is Jeb's velocity. This is Jeb's velocity between 37 seconds and 46 seconds. Okay, and since we define the positive direction as going away from the origin, the negative direction is going back to the origin, going back to the position of 0.
Here's the classwork. Please write these numbers down. As usual, these are going to be on the provided worksheet. See you in class.